So 4, 3, 2, 1. All right. So this is towards the common drain amplifier, what we were looking in the previous class. All right. So the essence of all we were doing last class, possibly I confused you all a little bit, is the following: that the common source amplifier, as we had made, right, is not really a voltage controlled voltage source. And the reason why it's not a voltage controlled voltage source is that if you calculate what its R out is, right, the R out of this particular amplifier is going to be your R0 parallel RL, right? If you include RL also inside the circuit, if you leave R0 out of the circuit, then it will just be, sorry, if you leave RL out of the box, then it will just be R0. It depends on where you are putting the arrow to look at this output impedance. In any case, R0 in the ideal case will be infinite. Now, a voltage controlled voltage source should have an output resistance which is low, right? The ideal voltage controlled voltage source should have a low output resistance. That's what we shaded in orange. So this particular thing does not behave like a voltage controlled voltage source. All right. And so, so as somebody pointed out here, we have already discussed what we can do, right? At least conceptually, we know what we can do. We have to make this buffer element. What the buffer element essentially does is, as we have drawn below here, using an op-amp configuration, the buffer essentially has a high input impedance and a low output impedance. So if you take your common source amplifier and connect it with a buffer, right, which has a unity gain, you will find that this whole thing, which is now in this other blue box, will behave like a voltage controlled voltage source. However, the problem is, how do you make that buffer? Right? The problem is, how do you make the buffer? We don't want to put an op-amp, because the op-amp itself is made up of all these amplifiers. So then it becomes a chicken and egg problem, right? So that's where we left. We left with the following fact, that assume that I have an ideal voltage controlled current source, which is what the MOSFET actually behaves like, right? The voltage controlled current source. Assume you have this ideal VCCS. How do you make it into all these four things? Okay. And the other degree of freedom that I am giving you is that I can pump this GM as high as possible. Okay. In the last class, what I said was that in order to pump GM high, you can do one of two things. You can either increase your IB or you can increase W by L. There's another way which I did not really tell you, which is that, sorry? No, with this formula itself, instead of just making W by L obscenely large, you can do the following, which is basically you connect many transistors in parallel. We have already seen how that works, right? So you can have, for example, one transistor like this, right? This transistor will have a ratio of W by L. Now, if I do the following connection, I take this here, right? And then, as we have discussed earlier, if I have an ideal transistor and that also has W by L, okay? And then I can repeat this over and over again. I take another guy and I connect something like that, right? So what does this net thing have now as I have drawn? This is 3W by L. If I connect it, if I have n blocks, I can get NW by L. I can get this as NW by L. Okay, so in principle I can get any GM that I want. Okay, we'll see later on that you cannot just cascade things like this. It will cause you some other problems. Yes, so there are a lot of, what Prasanna is saying is actually correct. If you remember, we drew this the Bode plot, right? So when you're doing this, what you're doing essentially is you're increasing the effective capacitance, because you're adding capacitances in parallel. So what will happen to your frequency response? It will shift. What was the lowest pole? It was RS and then CGS plus whatever 1 plus A times CGD, right? So if you keep pumping your CGS up, which is what will happen if you put everything in parallel, is that yes, your gain will go up, your GM will go up, however your bandwidth will decrease, right? So we'll come to that in more precise terms later, but in principle let's assume that you have infinite GM that you can play with. Okay, so let's proceed. Is everyone with me till here? Because otherwise you can lose me. So if you have questions, please ask, right? Okay, so now what I want to do now is that I want to make a voltage controlled voltage source. Okay, let's see if we can finish the voltage controlled voltage source today. Alright, so what is it that I want? What does a voltage controlled voltage source have? Okay, let me also qualify this further. I'll make things easy by saying that I want unity gain. Right? Because I know that if I want some other gain, what can I do? I can connect a common source amplifier before it, have whatever gain I want with that, and then connect this voltage controlled voltage source after that, and the net thing will give me a voltage controlled voltage source with high gain, right? So I'll just worry about a unity gain configuration now. Okay, because unity gain is easy to do. Alright. So now what do I so what does this mean? It means that if I have an input here, Vi, right? I should have an output VO, right? And this whole thing is what we are trying to make, right? This is your voltage controlled voltage source, and you want your VO to be equal to Vi. Okay, how can you make this? Can you do this? Can this box just be a short circuit? Do you gain anything by that? Okay, what are the other things that this voltage control voltage source should have? What should its input impedance be looking in here? It should be infinite, ideally. And what should its output impedance be looking in there? It should be 0. Okay, does your short circuit achieve this? No, right? If short circuit achieve these things, then we don't need to study analog circuits. So, right? So that's not allowed. Obviously, right? If that was the case, then no fun. Okay, and what do you have with you? We said that we are going to do all this with the MOSFET, and so which means you have the following incremental circuit element with you, which is, right, you have something that measures two voltages, and then it gives you a current which is dependent on that voltage. And let's assume for now it's an ideal thing, so we don't have any output impedance, we don't have any R0 there. Okay, this is what you have. Okay, and this is some GM times Vx, where this is plus minus Vx. Right, this is your MOSFET. Okay, now that you have this and I want that, how can you proceed? Okay, so now you have a current, so this is essentially a current source, right? So let's assume that you are going to think of it in the following way, and then you can help me. Okay, let me now, for fun, have a resistor. Correct. Why do you want a resistor? Because you are having a current source element there, right? So unless you have a resistor, you will not be able to convert the current into a voltage. So let me just connect some RL, right? Now again I have some input voltage, right? Let me call that as Vi. Okay, now also I have told you that I have this current source element, so let me draw the current source element there. And let me just pass that current through this RL. Okay, now if I pass a current, why are we connecting in series? Because what I want to do basically is that I want to take a current, okay, some current I, pass this through RL and then measure this voltage here and call that as V0. Okay, so the way I am going to do this is the following. Let me assume that this current source is actually controllable. Okay, so can now somebody with this and this, can somebody just verbalize what we are trying to do?
Controllable in the sense you need a regular current source.
No, it means that I can change the value of I. I have a knob, right? So, okay, let I pass through R. Let I pass through RL, okay, which implies that your V0 is essentially I times RL. Okay, then you compare V0 with Vi, right? If V0 is greater than Vi, what do you want to do?
Increase the current.
You should
Decrease the current.
decrease the value of I, and if V0 is less than Vi, implies you increase the value of I. Is that right? What will this kind of thing do? Right? If you do this, what will happen eventually if everything is working well? Right? So if this feedback works correctly, you will obtain V out equal to Vi. This will be independent of RL, independent of everything else that is there. Correct? So what you are doing is that you take this current, create a voltage out of that current, then you use that voltage and you compare it with respect to your input voltage. Correct? So if your input if your V0 is more than Vi, you have to reduce the current. If V0 is less than Vi, you have to increase the current. That's essentially what we want to do. Okay, now using this block on the left, using this block on the left and what I just described here, can you come up with a circuit? Think about it. Okay, all of you just draw something now. Think about it. Okay, who gets the answer first? Anyone with ideas?
Similar to what we did earlier, except it's just the quiz question, the last quiz question.
Yes, it is related to your last quiz question, but slightly different. So I have this block, right? So I'll just redraw the same thing in a slightly different way and it will become obvious. Okay, so I have my input voltage. Okay, did anyone have any ideas? Any ideas?
That's go to the gate.
Okay, now I'll have my thing here. Okay. Yes, same circuit. I'm not doing anything. Only thing is that I'm drawing it in such a way that it will give you a hint. What I've done is that instead of drawing V0 at the same line as at the same level as Vi, I have moved it down. Now does someone get a hint? Huh?
The output is taken from the drain.
Okay. All right. Now I need to control this, right? So what should I put here?
MOSFET.
Okay. Then, so your MOSFET needs a Vx So what should be my Vx? If Vx is VDD minus VI, then VI. Okay, so the question I am asking is I want Vx. So the options are VI, then somebody told me VDD minus VI, which doesn't make much sense because one is a incremental voltage, other is a this thing voltage. V0 minus VI. Good. Okay. What does V0 minus VI achieve? Right? So if you use V0 minus VI, correct? So if I call this as Gm times Vx, where Vx is this quantity, okay, what will happen? Does it satisfy what we wrote on the left hand side? How does it work? Right, if this point here, so in this configuration, where is your, now that you have put the transistor in there, where is my drain? That is drain, right? Where is my source? This is source. This is my gate. Okay, so now you look at this source, right? So if the current, whatever this current, Gm times Vx is the current, right? If this current is flowing in here, and if that current is, and the output V0 is nothing but, okay, so I have V0 is Gm times Vx. Vx is nothing but Vi minus V0. Okay, so now what happens if this current, no, is this right? Into RL. This is my current, right? So if this current, if this voltage here, what is V0? Yeah, right? This is V0. So if this V0 is greater than Vi, what will happen? Right? This will have a tendency, this Vs will have a tendency to come down. If Vs has a tendency to come down, what will happen to Vx? Vx will go up. Correct? If V0 comes down, Vx will go up. If Vx goes up, what will happen to current? Current will go up. So that will counteract the decrease in V0. So you see the negative feedback that's operating there, right? So if this is just to, if V0 decreases, then Vx increases. Yes. Correct. Yes. Good point. So we'll come there. We'll come there. That's why that other aspect you also need to use. That Gm is very large. Otherwise it won't work. Okay. So what I have written here is essentially that if you have V0, right, and if this V0 decreases by some chance, then this Vx increases, right, because Vx is nothing but Vi minus V0, right? Is that clear to everybody? Your Vx is Vi minus V0. So if V0 decreases, Vx increases, current increases, it has a tendency to compensate the decrease in V0. Okay, so this what we have drawn is essentially a feedback loop which implements what we described on the left. Okay, now let's take this and proceed further. Okay, so what we have essentially drawn then is the following. I have something like this here, something there, right? I have taken this voltage here, and then I have another voltage here. This I call Vi, right? That is Vo plus minus Vx. This is your Gm times Vi minus Vo, and then I take this and pump it up to, this is in the incremental circuit, so that will also be ground. Okay. Now can you write out what is Vo here? Can you solve for that? What did we just say? We said that VO is GM times VI minus VO into RL. Okay, simplify this. That will be GM VI RL minus GM VO RL. So VO into 1 plus GM RL is VI into GM RL, which means that your VO is VI into GM RL divided by 1 plus GM RL. Okay, now can you tell me what should happen here? How do you design your GM and RL and all of that?
GM must be much greater, so V should be VI.
Okay, so this is a standard thing that we have, right? We write some expression. What do you want? We want V0 to be equal to VI. Implies what should you do to GMRL? You make GMRL much greater than 1. Okay, or your GM is much greater than 1 by R. Alright. So this is the incremental circuit. Okay, and where are you taking the output? You are taking the output, drain, source and gate. You are taking the output at the source. Now out of the gate, drain and source in the incremental circuit, which of these terminals is ground? Which of gate, drain or source are ground in the incremental circuit? Drain. Drain is so this thing is called a common drain amplifier. Right? Go back. In your common source amplifier, which of gate, drain or source was connected to incremental ground? Source, right? Go and check your common source amplifier circuits. Where do we have that? This is your common source amplifier, right? The common source amplifier, where is the source terminal here? Right? This is your source terminal, this is your gate terminal, that is my drain terminal. So in the common source amplifier, source is connected to incremental ground. Common drain amplifier, drain is connected to incremental ground. Common gate amplifier, which we haven't yet seen, but we will. What do you think will be connected to incremental ground? Gate. Okay? Yes? No. By incremental ground, I mean that ground in the incremental circuit. Okay? Just terminology. Instead of reading out that entire long list of words. Okay? Alright. Now, what more do I need to do to make my common drain amplifier? So, you have made your incremental circuit. What should you have along with your incremental circuit? Bias circuit. Okay, so we need to create the bias circuit. For the common drain amplifier. Okay, now which of the bias circuits do you think we should use? We had a discussion on this, right? So we discussed these various bias circuits the other day, right? I mentioned that you can use any of these bias circuits, right, for any of the amplifier types, right? All of these use a current to set up the operating point. As a result, they are less sensitive to process variations in various parameters, less sensitive to temperature and things like that. Okay, so now out of these three options here, which do you think is the most which do you think we should use? Okay, again, as I have stressed earlier also, you can use any of these to make the bias circuit, right? You might have to include some big fat capacitors and big fat inductors in some place. Okay, otherwise you will not be able to make any one particular circuit look like an elephant for AC and a donkey for DC, right? In order to make that thing, you will have to stick things into it, like a clown's hat. So instead of clown's hat, you put like capacitors and inductors, right? So, however, if you are given the choice, you might want to take one which is the easiest for you to use. Okay, now look at these three, right, or four actually, and tell me which is the one that you think will be most appropriate for the bias circuit for the common drain amplifier. 3B. Okay, why? Okay, let us not go to 3B first. Okay, 3B is essentially an approximate version of 3A, right? 3B is 3A where you, instead of this current source, you put it with a large resistance. Okay, let's take only 3A, 2 and 1. Which has two current sources? 3A has two current sources. Why? All your circuits have two current sources in the incremental circuit. Each of these MOSFETs is a current source, right? What is that current source that we drew here? This GM, this is coming from your MOSFET, right? Okay, let's draw this thing in another way. Okay, let me see if I have space. This same thing, okay, if I were to draw it with a MOSFET, how will it look? I have that, right? What happens to the drain? Drain is connected to incremental ground. What about the source? Source is connected through a resistance. Okay, anything else I need to do? Do I need to give that? It's implicit there, right? It's implicit because this thing Vx is going to measure the voltage between G and X and this source, right? And okay, very colorful. Okay, and have I finished? I have to connect my what feedback? Think about it again. Right? This and this are identical. I don't need to give any more thing for feedback and all that because the feedback is, see, it's going to take Vx. Vx is nothing but Vg minus Vs. And okay, one other thing you have to do, which is you will tell me where to take the output. Where is the output? That is my Vo. Okay, so all right. So now what I can do is I take this and just reduce it. No need, I can take this and reduce it. Alright, so any ideas now? Go back and think about those various biasing circuits. And what I'll do is I'll copy this here. Right. So what you have here downstairs is the incremental circuit, right? So ideally, how do you want to choose the circuit?
So that I don't mess up with the source.
Right. So basically, what you want to do is you should make one big circuit, which for the incremental picture will look like this incremental circuit, and for the bias picture will look like one of these things that I have drawn above. Okay. Now, if I want that, which of these should I take such that I can come up with one circuit and without adding too many inductors or capacitors, it looks like the incremental circuit for the incremental analysis and like the bias circuit for the bias analysis. 3A. Why? Because you don't want inductor or capacitor. Okay. 3A is the answer, but try and justify it in a better way.
So the resistor at the source will act as a current source sitting the
Alright,
sitting the source.
that's one way, but think more carefully. What is the distinguishing feature of the common drain amplifier? Can you comment about its source terminal? The source terminal of a common drain amplifier, is it connected to incremental ground? No. Correct? It's the drain terminal which is connected to incremental ground. Now look at these various biasing circuits and tell me, based on this fact, whether you can choose 1, 2 or 3A. Why? No, you still not hit the nail on the head. Okay, let me take 2. Let me take circuit 2. In the incremental picture for circuit 2, what will happen to the source?
It will remain there.
It will?
Open.
No, take circuit 2. In circuit 2, the source, where is source? That is source. This is source, right? Gate, drain. Similarly, source, gate, drain. Okay. In circuit 2, what happens to the source in the incremental picture? It will be connected to ground. Okay. What do you want? You don't want it to be connected to ground, right? So now you have a situation where in the incremental picture something is getting connected to ground. So, if you used source 2, which was drain feed, if you used circuit 2, which was drain feedback, right? However, you do not want that source to get connected to ground. So you can manage. You will have to put, what should you put there? Capacitor? You will have to put an inductor in series, because if you put an inductor in series, for omega equal to 0 it will be a short, but for your whatever frequency of operation, it should give an infinite, rather it should lift the source from the ground, right? So you will need to choose a large L. Okay, alright, that's a problem with 2. What about 3?
3 will give an infinite resistance.
Which is good, right? So basically in 3, so circuit 2, right? If you took circuit 2, your source gets connected to incremental ground. In circuit 3A, source is open incrementally. What does open incrementally mean? What is the incremental circuit for this guy? If I take 3A,
VDD on the top go to incremental grounds.
okay, now I want you to I want people to draw the incremental circuit for this. Okay, this is my bias circuit. Okay, what would be the incremental circuit? Only of this. Okay, what will happen? What should happen? Both the resistors. Okay, then that thing goes to MOSFET. Okay, then what happens to drain? Drain goes to ground. Okay, what happens to the source? Why? Because the current source is killed. Okay, so this becomes the incremental circuit for, yes, right? This is the incremental circuit for 3A. Now to make the amplifier, you should take 3A and then give the input signal and then take the output signal and then see what happens to the full incremental circuit. But at least what I am trying to say on the previous page, right, that in case 3A, this source, if you take 3A, then the source in the incremental circuit is floating, and that is useful, right? Or look at it the other way around. Floating means that, alright, or look at it the other way around, which is if you took this If I took 2, okay, let me take circuit 2. And then do the same thing. What will happen? I want to have 2, so I'll move that. Oops. What can I do? Okay, think about how do you draw the incremental picture for this, for circuit 2. Then you will know, it will become obvious. Oops. It's become very large, the PDF. Okay. Okay, this is circuit 2. This is circuit 3A. Okay. Now for circuit 2, if I want to draw the incremental picture, what will it look like?
The ground is short.
Okay. I have my MOSFET. Okay, tell me, Rajat, what happens to this in the incremental picture? This RDG will remain, right? Anyway, RDG does not really trouble you too much, so let that remain. Okay, what happens to this? This remains open. Why? Because you have removed the current source. Okay, and then what happens to source? Source is connected to ground. Okay, so this is open here, and that is your drain, that is your gate, this is your source, this is source, that is open, gate and drain. Okay, now does it become clear to you? Okay, what is it you are trying to do? We are trying to have an incremental circuit, right, whose drain is connected to ground and whose source is not connected to ground. Because if it is not connected to ground in the incremental circuit, you can add something in the incremental circuit that makes it connect to ground through something else, through this RL. Correct? However, if the source of your biasing circuit is such that it gets connected to ground automatically in the incremental circuit, then it is not what you want, right? Because in your incremental circuit, you do not want your source to be connected directly to ground. Do you get that? Still, I see lots of blank faces. Do you get what I am trying to do? Okay, think about it, right? I am just trying to choose one of these bias circuits as my biasing circuit to make the common drain amplifier. Yes, 3A or 3B, there is no problem. I said that 3B is nothing but an approximate version of 3A. Okay, so 3B is also good, no problem. Okay, 3B is perfect. 3A or 3B is okay. But if you choose 1 or 2, right, then the incremental circuits corresponding to 1 or 2 will be like this, right? If you took 2 for example, in the incremental circuit the source is connected to ground. However, you want an incremental circuit where source is not connected to ground. So for that you can choose either 3A or 3B, which give you, if you took 3A then you get source which is open. If you took 3B then you will get a source which is connected to some resistor to ground. No problem. You can make that resistor your RL. Okay. Again, you have to choose things correctly, right? You can also do funny things like you can put a capacitor and then bypass a portion of that resistor, right? You can do all kinds of things. Okay. But in general it allows you to play. Alright. Again, I see lots of blank faces. Think about this. We can discuss this again. So I am going to go with, okay, I am going to go with 3A. Choose 3A or 3B for the biasing arrangement. Okay. Now let me see which one I have actually used. Yes. Our aim is to create a buffer. Correct.
The main reason we started creating buffer is like when we connect something else to there will be current going.
Correct.
And V out itself will change.
Correct.
So, but now also we see.
Okay, let us analyze that. Let's analyze that aspect of the circuit. Let's finish the biasing arrangement and then we'll analyze whether this circuit actually works like a buffer or not. Okay. But if you go back to how we verbalized it, right, we did not think about any input impedance, output impedance and all of that here. What we said was, you take an input, you compare it with what you want, right? If it is not what you want, basically what you want is input itself, right? So you have Vi, you know your VO should be Vi. If it is not, you pump in more current. So the way we have said, at least describe the problem, we did not mention what the input impedance, output impedance and all of that should be, right? So if you have a very large RL, then in order to make these changes, you have to pump in much more current. That's all, right? So let's see how that works when we do the analysis finally. But let's proceed and finish the full circuit. Okay. Okay, so how do you think the full circuit will look if I use 3A? Okay, so this you should be able to draw very quickly. I have my transistor. 3A means that I have a current source. Correct? Then what do I have above here? Just your VDD, right? And then in 3A there was you had two resistors here. Why were those resistors? No, they are voltage dividers, but what was the purpose? How does this bias circuit work? What is kept fixed and what is allowed to change? VG is kept fixed, Vs is allowed to change, right? Based on what your IREF is, right? So I'll call this as IREF. Okay, that was my biasing circuit, 3A. Now how should you connect things? My source, again, like we have discussed earlier, connected through an infinite capacitor, source resistance and a source voltage, right? I call that Vi. I don't want to use Vs because I have a source okay. So when I mention source, be careful. It can either be the voltage source or the source terminal of the MOSFET. Okay, be careful. From context it will become clear. Just to avoid any confusion, I am using Vi for the input voltage. Okay, so we'll call it input voltage or source voltage. Alright, where should I take my output? At the gate. So this is that is gate, that is drain, that is source, right? Now I should take the output at the source. And what do I want? Okay, I want this to be my incremental circuit, right? I want this to be the incremental circuit. So just keep that in mind. So what should I do to this full circuit in order to get this RL in now? I put a capacitor and then RL. And then I take my output V out here. Okay. Now the same circuit if I wanted to do with 3B. What should happen with 3B? Right? So I can, for 3B, this thing IREF will change, right? And this is using 3B. Okay, only change is that I have a resistor here. I can call that resistor as R what? Let me call that RE. Okay, and now this capacitor essentially allows you to include a different value of RL. You can also have a situation where you bypass your RL, where you remove RL and just have RE. Make RE your RL. But what will happen in that case? No, it won't change your GM. In that case, your load. No, in that case your load will also take the DC current. Right? What I am discussing is the following, that if I
The capacitive effect won't be there. Decoupling effect of the capacitor.
if I move that out there, okay, and say that this is my full circuit without this capacitor and everything, then what will happen? Your RE will perform the job of your load. However, the DC current will also flow through RE. Maybe some loads are okay with it, some loads don't like it. Like if you take a speaker and pass just DC current through it, then it will make a big hum, and then all whatever I am talking will come over that hum. Right? You don't want that. So if you don't want that, then you can just have this thing back there, right? Some RL dash, no problem. It's okay. Right? Because in that, when you short this, RE parallel RL will become your effective RL dash. It's okay. Okay? Alright. Now, so this thing is your common drain amplifier. Okay. Okay, now the question which Ankit asked, which is very important. Which is for this particular circuit, right? I want to calculate my input and output impedance and my gain. Let's take this one, it's easier to analyze. The other one is also equally, yeah, I'll do it for this. I'll give the other one in the quiz. Assignment, where am I cooking up assignment problems? I'm very slow on that. I should give you more assignments. Yes?
For this circuit incremental,
Ah.
such that VG should be EBI. But if we are selecting for this, then that resistance should be.
That resistance will be there, no problem. We'll see that. The resistance won't trouble you. Okay, the resistance won't trouble you. Why? Okay, let's take this and now draw the exact incremental circuit for this, because you have included this resistance and all of that, and let's assume that this MOSFET were not an ideal MOSFET, it had an R0. Okay, let's just draw the incremental circuit for this. How will the incremental circuit look to satisfy everybody? Okay, so I have my signal source, I have my RS, okay, signal source RS, alright, then I have my favorite RA parallel RB, then what else do I have? I have that guy, and then what connects here? RL itself, right? Because this IREF disappears and RL gets introduced. Okay, then what else do you have? What happens to this? Okay, that is ground. And in addition, I wanted to be nasty, I wanted to include something. What was that? R0. Where does R0 go? So this is drain, source, gate. So where will your R0 go? Right? R0 will go only up to that. Right? Okay. Now can you calculate what VO is in terms of VI quickly?
Assuming RA parallel RB greater than RS.
Yeah, we'll come to all of that. That's standard, right? That one we'll always want. Yeah, you can make that approximation. Okay, calculate. Don't. So let me call this voltage Vx. Okay, this will be Vx minus Vs. Okay, or to be a little cleaner, because your Vs is nothing but V out, right? Where's the output voltage here? So I'll call that as that minus that. Okay, somehow my handwriting R and V are looking similar. It's not. What? Yes, that V out is wrong there. I got so used to common source amplifier that V out is coming there, right? That V out was 0, right? Okay, can you analyze this? How do you proceed? How do you proceed? Okay. All right. So basically, look at it this way. One, you can do it in many ways. Okay. First thing we'll do is we'll do the usual trick. The usual trick, we'll say RA parallel RB to be much greater than RS, which means that your Vx would be equal to Vi. Okay, that's a common trick we are doing everywhere. All right, then what happens now?
Now it's parallel circuit.
Okay, so there's VO here. All right, this is that. Okay, analyze this and get me the following answer. Okay, VO will be Vn into GM RL parallel R0 divided by 1 plus GM into RL parallel R0. Okay, prove this. Okay, prove that, and I'll also tell you two other things to calculate because that's very important. Please do it for the next class. Okay, for this thing, calculate what my input and output impedances are, and in order to say that clearly, what am I going to do? What I'll do is I'll just move this. Yeah, I'll draw this in a slightly different way. Okay. Okay. No, I want to take RL there, right? And that is V out. Nothing. I didn't do any change. I just moved that a little bit that side, and I'm going to take all of this as my amplifier. Okay, all of that is my amplifier. What I want is you to calculate what is R in here, okay, and what is R out here. Okay, okay, R in is nothing but RA parallel RB. Okay, so at least that aspect, can you make a comment? What do you want R in to be? You want it to be infinite. Can you achieve infinity?
Yes.
Why? Because RA and RB, there is no problem, right? The only thing that matters about RA and RB is the ratio. Absolute value, I can push to infinity, no problem. So for the voltage control voltage source, so this whole thing should be your voltage control voltage source, right? So what do you want? So VCVS implies you want R in tends to infinity and R out tends to 0. Correct? Alright. So now you calculate R out. How will you calculate R out? Be careful, be careful. Be careful. Okay. So to calculate R out, what we do? Yes, right? So to calculate R out, you basically remove this thing, right? Instead, you connect a V test here, remove the input source also, pump in that V test, go through the loop, calculate what I test is, and find out what R out is. Okay, and do that for the next class. It's important. All right, that is because that's where the trick is. So once we have gain, input impedance, output impedance, what mode should you calculate? Swing limit and frequency response. Okay, so we'll do those things possibly in the next class.
Take the impedance
Correct.
So this is probably got in the flight.
No. Because the way we verbalized how this whole thing works, right? We didn't care about the input impedance.
Yeah, we didn't care about it.
Yes.
The aim of the second switch was that we get impedance.
The aim was to make a voltage controlled voltage source. And we verbalized what a voltage controlled voltage source should mean.
Problem set, the same statement didn't have independent impedance in consideration.
It does not matter at all, because if you have a voltage controlled voltage source which behaves in the way we verbalized, automatically the input impedance will be infinity and output impedance will be 0. Because what does it say? It says that irrespective of what load you put, the circuit will change itself to give you the output voltage what you want, which means it does not matter about what the output load is, or in other words, the output impedance of the source is immaterial. Okay, or rather not immaterial, it will be very low, so that irrespective of what load you put, it will not, you will get,
Less than that.
yes, right? Yeah, so we'll see that. So calculate the input and output impedances for the next class. Okay, all right, thank you.